Good morning everybody. Today our topic of discussion is binary liquid systems. In this module we have included the topics vapor pressure, Raoult's law, ideal and non-ideal solutions, solubility of liquids in liquids, their different types and Liver rule. So first of all let us discuss about vapor pressure of a solvent. So vapor pressure, as you know, if we keep solvent in a beaker, in a closed beaker, the molecules of solvent will start evaporating. At the same time, the molecules will also undergo condensation process. So there are two processes are going simultaneously. One is evaporation and other is condensation. So when these two processes are acquiring a dynamic equilibrium, the pressure of the vapor which is in equilibrium with the liquid is called the vapor pressure of that particular solvent. The vapor pressure has great significance when we consider the volatility of a solvent. As you know, if we are keeping ethanol in one beaker and water in another beaker, which will evaporate faster? All are aware that ethanol will evaporate faster because the vapor pressure of ethanol is much higher than that of pure water. Another important significance of this vapor pressure concept is with the boiling point. If we, as you know, boiling point is the temperature at which vapor pressure becomes equal to atmospheric pressure. So, if the vapor pressure of a solvent is higher, that means we need to apply only small energy to make it equal to the atmospheric pressure. So, the boiling point of ethanol is much, as the vapor pressure of ethanol is higher, the boiling point of ethanol will be lower than that of water. Okay. All solids and liquids have a vapor pressure, but the vapor pressure of solids is much less compared to that of liquids because their evaporation is less, as you know. Now let us discuss about the vapor pressure of solution. Solution means if we add a solute, non-volatile solute to a solvent, or if we are mixing two different type of solvents. So, in the case of a solvent, when we add a non-volatile solute, vapor pressure decreases because if we are adding non-volatile solute, some of the solute molecules are occupying the position of the solvent molecules. So, evaporation starts from the surface of the solvent layer. So, number of molecules at the surface of the solvent will be reduced on the addition of solute. So, the vapor pressure exerted by the solvent in a solution will be less compared to the pure solvent. So, the lowering of vapor pressure in a solution is studied by a French chemist Raoult. He expressed this law as the vapor pressure of a solution, that is P solution, is equal to a chi solvent, that is mole fraction of solvent, into P0 solvent. P0 solvent means vapor pressure of that pure solvent when it is present alone. So, the same law is shown graphically as shown the right hand side of the slide. Here you can see in the x axis we have given mole fraction of the solvent and the y axis we have provided the vapor pressure of the solution. So, the graph, it is clear from the graph that with increase of mole fraction of the solvent, the vapor pressure of the solution goes on increasing. And another important point about Raoult's law is that this law is obeyed by dilute solutions only. And the solutions which obey Raoult's law is called the ideal solutions. Now let us discuss in detail about the ideal solutions. These solutions are solutions which obey Raoult's law at all concentrations and temperature. So, in order to form an ideal solution, the mixing components should have identical structures. So, in this type of solutions, the interaction between identical molecules and non-identical molecules must be of equal strength. Here we can see if A is one type of solvent and B is another type of solvent. So, AA interaction approximately same as BB, which is again same as AB interaction. So, since the molecular structures are identical, on mixing the two solvents, there is not much difference in not much rearrangements are required during mixing. So, delta H mixing that is heat change during mixing will be equal to 0 for an ideal solution, and similarly delta V mixing is also 0 for an ideal solution. Now let us see some of the examples of an ideal solution. Normal hexane and normal heptane. You know that their structures are almost similar, hydrocarbons. So these two form an ideal solution. Another example is benzene and toluene. They are also, structures are also identical. So this also forms an ideal solution. So coming to the next slide, here we have discussed about vapor pressure composition graph of an ideal solution. Ideal solution means solutions which obey Raoult's law. So in the right hand side, I have given a graph. So we have to look in detail into the graph. Here in the x-axis, we have given xa equal to 1 and xb equal to 0. That means only one component is present at the left hand corner, that is A is only present. So the vapor pressure corresponds to P0A, that means vapor pressure of the pure component. In the right hand side, we have written that xa equal to 0 and xb equal to 1. That means only one component is present, which is B. So the vapor pressure corresponding to pure B is P0B, which is shown there. So from the values of P0A and P0B, you can understand that the vapor pressure of A is much higher than that of B. So that indicates A is more volatile compared to B. Okay, now we can discuss about the change in the graph, that is the dotted lines or lines plotted in the graph. You can see two types of lines. One is green line and another is the black bold line. So when we move from xa equal to 1, that is from the topmost corner, topmost side, if we are moving, that is we are adding B to A. So what happens? The mole fraction of A in the solution decreases. So the graph, green line, graph means partial pressure of A decreases, and when we move from left side to the right hand side and it reaches xa equal to 0. That is when A is 0, the P0A is also 0. Similar is the case with the P0B, that is if we are moving from the right hand side to the left hand side. There initially B is only present, we are adding A to B, that means the mole fraction of B is decreasing. So the partial pressure of B goes on decreasing when we move from the right hand side to the left hand side. So these two green graphs are explained, and these graphs correspond to the equation of a straight line. As you know, according to Raoult's law, PA, that is vapor pressure of a component, PA is equal to P0 into XA. That equation follows the equation of a straight line. And now let us discuss about the black bold line on the top, which is P is equal to PA plus PB. That means the total vapor pressure of the solution. So the total vapor pressure is the sum of the pressure exerted by the individual components A and B. So that is why we have written P is equal to PA plus PB. This is obtained by connecting P0A and P0B. So now let us discuss about real solutions or non-ideal solutions. Real solutions means they do not obey Raoult's law. These type of solutions are of three types. First type is they show small positive deviation from Raoult's law. For example, benzene and toluene. They show small positive deviation from Raoult's law. Second category, type 2. They show large positive deviation from Raoult's law. For example, water and propanol, or we can say water alcohol combination show large positive deviation from Raoult's law. Third one, type 3, show large negative deviation from Raoult's law. For example, acid water, water nitric acid or water sulfuric acid combinations. Now let us discuss the deviation, that is two types of deviations we have mentioned. One is positive deviation and another is negative deviation. Now let us discuss about these deviations in detail in the coming slide. So this indicates positive deviation from Raoult's law. Positive deviation from Raoult's law means the vapor pressure exerted by a component is much higher than that predicted by Raoult's law. That is PA is greater, here you can see PA is greater than P0 into XA. P0 into XA means the vapor pressure of A according to Raoult's law. Here since the solution is showing positive deviation, PA is greater than P0 into XA. And similar is the case with the PB. PB is greater than P0B into XB, which is the predicted value according to Raoult's law. Here you can see the graph here. Similar graph we have discussed earlier. X-axis is A and Y-axis only B is present. P0 is the vapor pressure of pure component A and P0B is the vapor pressure of pure component B. So the dotted lines represent the graph as per Raoult's law. This is the graph we have discussed in the previous slide. And in addition to the dotted line, here you can see a deviation, that is a graph in the going upside to the dotted line in all components, that is for PA, you can see PB and also the total vapor pressure. So these show that the solution is showing positive deviation from Raoult's law. And in the case of a solution showing positive deviation, we have to express in terms of molecular interaction. The solvent-solvent interaction, here you can see A-B interaction, that is interaction between unlike molecules, is less than interaction between like molecules, AA or BB interaction. So the enthalpy of mixing, delta H mixing will be greater than 0 because the heat absorbed to form new molecular interaction is less than the heat released on breaking of original molecular interaction. Similar is the case with the delta V mixing, which is also greater than 0 since the volume expands on dissolution of the components A and B. Next, let us discuss about negative deviation from Raoult's law. So negative deviation means the vapor pressure of component is less than that expected from Raoult's law. The value expected for A from Raoult's law is P0A into XA. So here PA will be less than P0 into XA and PB will be less than P0B into XB. And the total vapor pressure, that is P0 into XA plus P0B into XB, is less than that is expected in Raoult's law, which is PA plus PB. Here the solute to solvent interaction is stronger than solute-solute and solvent-solvent interaction, or we can say in other terms AB interaction, that is interaction between unlike molecules is much higher than that between identical molecules AA or BB. And in this type of deviation showing solutions, the enthalpy of mixing, that is delta H mixing, is less than 0 and delta V mixing is also less than 0. Here the graph is plotted here. Similar is the earlier graph. Left hand side is P0A, right hand side is P0B, and the dotted line indicates the graph corresponding to ideal solution, that is solutions which obey Raoult's law. Here you can see this type of graphs which is less than the which is going below the dotted line. So this indicates that the value of vapor pressure is less than that predicted from Raoult's law. Next, let us discuss about the limitations of Raoult's law. So the first limitation, as we have already discussed, this law is apt for describing ideal solutions. So you know that ideal solutions are very hard to find out in our real situation. So this is a limitation. Second is that since many of the liquids that are in the mixture do not have the same uniformity in terms of attractive force, these type of solutions tends to deviate away from the law. And the third one is that there is either a positive or negative deviation, as we have discussed in the previous slides. Negative deviation occurs when the vapor pressure is lower than that expected from Raoult's law. Example of negative deviation is a mixture of chloroform and acetone. So chloroform acetone combination shows a negative deviation from Raoult's law. Or similarly, positive deviation also takes place. This happens when the cohesion between similar molecules is greater or that it exceeds adhesion between unlike or dissimilar molecules. Example, you can see positive deviation, benzene and methanol, ethanol and chloroform. These are the normal mixtures that show positive deviation from Raoult's law. So now here we have discussed about the Raoult's law, its solution showing positive or negative deviation. These are the factors we have discussed. Now next topic is the solubility of liquids in liquids. So here we have discussed about three types of liquids. First one showing complete miscibility. For example, water and ethanol. You know that if you add water to ethanol, it will appear as a single layer. So that means it is completely miscible. Second category, complete immiscibility. For example, water mercury. You know that if you add mercury to water, due to the heaviness of mercury, it will drop down at the bottom of the beaker. So it will appear as two layers. Mercury and water appear as two layers. So it means they are immiscible. Third category is solution showing partial miscibility. For example, water and phenol. Chemistry students are doing practical in their physical chemistry with water and phenol in their partial miscibility. So, water and phenol, if you add, you can see slight turbidity. That means they are partially miscible. So, here you can see the components of an ideal solution will be miscible in all proportions. Such complete miscibility is also observed in some real binary systems, for example, ethanol and water under normal conditions. You know that if we add ethanol to water or water to ethanol, it is completely miscible. Second, you should note that attraction between molecules of one component are greater than those between its molecules and those of the other component, or you can say 1-1 interaction is greater than 1-2 interaction. That means interaction between like molecules are much higher than the interaction between unlike molecules. So, if a positive deviation from Raoult's law occurs, the miscibility of the components can be reduced. Another point is that the greater the strength of self-association, the greater the immiscibility. Because if you say, if you are consider two components A and B, if you are adding A to B, so if the interaction of AA interaction is much greater than AB interaction, that means the molecule has more affinity to itself only. It is not related, or it does not like to add the other component, interact with the other component. So, this is the case discussed here. Greater the strength of self-association, greater is the immiscibility. Greater the degree of positive deviation from, then the greater the degree of positive deviation from Raoult's law. For example, water and mercury binary system. So, the degree we are discussing about the degree of miscibility. So, degree of miscibility is greatly dependent on a factor called temperature. First case, solubility increases with the increase in temperature. So, this is the case we are facing with the water and phenol. If we are adding water to phenol, as I already said, the mixture will be slightly soluble, that is partially miscible. So, if you are increasing temperature, the solubility of water and phenol with each other increases. Second case, solubility decreases with the increase in temperature. Water triethylamine combination. In this case, solubility, if you are increasing the temperature, solubility goes on decreasing. And the third category, solubility increases with the increase and decrease of temperature. This is a rare case, water nicotine system. In the case of water nicotine system, with the increase of temperature, miscibility increases. Similarly, with the decrease of temperature also, miscibility increases. And the fourth category, solubility not affected by temperature. So, there are some systems here there in which their solubility is not at all affected by the effect of temperature. Now, here we are discussing about the effect of temperature on miscibility. Effect of temperature variation depends on the degree of miscibility in the systems is described by means of phase diagram. That is, effect of temperature on the miscibility of two systems can be expressed by means of phase diagram. So, let us discuss what are phase diagrams. Phase diagram means graphs of temperature versus composition at a constant pressure. So, first here we are discussing about systems showing an increase in miscibility with the increase of temperature. A positive deviation from Raoult's law due to difference in the cohesive forces that exist between molecules of each component in the liquid mixture. Here you can see with increase of temperature, that means positive deviation decreases and miscibility increases. Each phase consists of a saturated solution of one component in the other liquid. Such saturated solutions we call as conjugate solutions. Okay, here we are discussing about the first category, that is miscibility increases with the increase of temperature. As I have told the example, it is phenol water system. Here you can see a graph connecting graph in which temperature is plotted in y-axis and the percentage of phenol is plotted in the x-axis. So, you can see a curve starting from the initial percentage of phenol. It is rising up and reaching a maximum and again decreasing. Here it means with increase of temperature, the miscibility of phenol and water increases. Here you can see a line BC connecting, drawn across region containing two phases, that is termed as a tie line. That is, BC is a tie line. It is always parallel to the baseline in two component systems. All systems prepared on a tile line at 50 degrees Celsius will separate into phases of constant composition whose composition is B, and here we have represented as B and C. These phases are termed as conjugate phases. So, here we are discussing about the critical solution temperature or upper consolute temperature. It is the maximum temperature at which two phase region exists, that is phenol and water exists. In the case of phenol water system, this value is 66.8. This means all combinations of phenol and water above this temperature are completely miscible and yield only one phase liquid system. So, above 66.8 it appears as only one component system, one phase system. Now, we are discussing about systems showing decrease in miscibility with the increase of temperature. For example, a combination of triethylamine and water showing this type of graph. Here you can see in the y-axis we have plotted temperature and x-axis the composition of triethylamine is plotted. As you can see, initially when we add water to triethylamine, there are two phases. As we said, with the increase of temperature, this system shows a decrease in miscibility. So, here you can see with the increase of temperature, the two phase system it is going down, that is the miscibility is decreasing, and at the when the temperature is decreased, finally it is merging into one phase, that it is shown here, a parallel graph is shown, that means one phase is existing. So, the solubility of liquid phase may increase as the temperature is lowered, as said in this case. So, this type of systems are said to possess lower consolute temperature. Below this temperature, the two members are soluble in all proportions, above which two separate layers are formed, or they exist as two phases. So, here we discuss about the third type of system, that is, as I said, some systems of combination show increase of miscibility with increase of temperature, and also with the decrease of temperature also miscibility increases. So, here we have discussed about a nicotine water system. Here you can see the graph. In the x-axis we have plotted the percentage of nicotine in water, and y-axis temperature is plotted. So, you can see this type of combination show an upper and a lower consolute temperature, that is, with increase of temperature miscibility increases, and with the decrease of temperature also miscibility increases. So, there are two types of values of CST, upper consolute temperature and lower consolute temperature for this combination. Systems, and the fourth category is systems with a no critical solution temperature, that is, temperature does not have much effect on the solubility of such systems. The pair ethyl ether, diethyl ether and water has neither an upper nor a lower consolute temperature and shows partial miscibility over the entire temperature range at which the mixture exists. So, we have already discussed about the effect of temperature on miscibility of liquid systems. Now, we are discussing about the effect of solutes or additives on the CST. So, there are different systems are shown in the table. First one is type of system showing upper CST. In the case of an upper CST, if we are adding a solute which is soluble, approximately equally soluble in both the components, then the CST will be lowered. But similarly, if the solute is soluble in only one of the components, then the CST will be raised, that is, CST value will increase. And with a lower system possessing lower CST, if we are adding a solute equally soluble in both components, the CST value will be increased. And another factor is that if the solute is soluble in only one component but not in the other, then in this case also the CST value will be lowered. Okay. Now, we have discussed about the different parameters of the partial miscibility of liquid systems. In the coming slides, we will discuss more detail into this topic. Okay, thank you everyone for watching this class.